Okay, in this PowerPoint, we're going to go over the renewable energy sources. That includes um, solar energy, wind energy, wave energy, and the other one, hydroelectric. Okay, as a quick review, don't forget that power is equal to work over time, or in other words, work is how much your energy changes. So change in energy per unit time. We're going to use that a lot in this PowerPoint. Now we are going to learn about wave energy. Okay, one of the most common ways that they get wave energy. There's lots of different methods that they use. They want you to know specifically about a thing called an oscillating water column, or OWC. Okay, an oscillating water column works in the following ways. So here is your oscillating water column. Okay, and as the wave over here comes in, watch what happens. So as the wave comes in, the water is pushing up the water level in the oscillating water column. Okay, and you'll notice as the water goes up, it's pushing this air out. And as it pushes the air out, it opens a valve here, the air comes through and then comes out. And this is a turbine right here, a little fan blade that as the air is being pushed out, it will spin this and then create electricity. Okay, and then when it gets to its peak, right, the water will stop going up and then will actually start coming down. As it comes down, it will suck these valves closed and it'll stop those openings, okay, and then it will try and suck or air back in as the water falls down. So then air is sucked in again through the oscillating water column, through that turbine, and then is pulled back down. So it's pushed out and then pushed in, and then pushed out and then pushed in, and each time passing by that turbine creating electricity. Okay, now that we know how an oscillating water column works, let's go over the actual calculations for wave energy. Again, we start with gravitational energy of the wave, because the wave, as it's coming in, that water is nice and high, right? So it has gravitational energy. And as that wave comes in, right, it starts to push the water inside the oscillating water column up. Okay, so the gravitational energy of the wave actually gives the water kinetic energy and lifting that water in the oscillating column up. The water moving up pushes the air, so it gives the air kinetic energy. The air then spins the turbine. Some of the energy will be lost because the air is still moving, and then that turbine spinning will then generate electricity in the generator. Okay, the pros and cons of wave powers are as follows. Like all of them, it's free, right? You don't have to pay for waves. You get reasonable energy density out of each wave. These waves have a lot of energy in them, especially if you look at the whole wave along a beach, like the whole length of the wave, the width of the wave along the beach. Okay, and it's also inexhaustible. It'll keep on going. Waves always come. And of course, it's clean, meaning it doesn't emit carbon dioxide and other greenhouse gases. Some cons include the fact that it only works in areas with large waves. There's not a whole lot of areas like that, and even when it is, usually our cities, we don't build cities close to areas with large waves, so it's usually, again, far away from cities. Also, waves are kind of irregular. The patterns sometimes, right, you can have choppy water and different kinds of things that'll make it irregular and then make your ability to get electricity inefficient. Also, the maintenance is quite expensive, and the installation cost, especially because, remember, this works in areas with large waves, and so that means these machines are getting kind of pounded. And also, it can be costly because of storms, right? It could be in areas where there's a lot of storms and things like that. And again, like I said, because these areas with high waves and large waves are usually far away from the cities, and you have to pay quite a bit of money to make sure it's transported over to a place that is usable, and that can be costly. Oh, and the last thing, you have to watch out for like hurricanes and stuff like that, because, right, that's where all the hurricanes are, is on the ocean and then coming into the land. How do you actually calculate the energy or the power from wave energy? This is actually a little strange. It took me a while to figure this out. So what we're going to do is we are taking this energy per unit time, and we're saying, okay, what is the original amount of energy? And it's actually the height of the wave. Okay, and the weird thing about this whole thing is that in order to make this equation work, it's quite forced. Okay, so take it with a grain of salt. We're going to say, okay, we're going to lift some of this water up. So here we have a picture of water, or a chunk of water, but this is when it's calm, right? So in order to make waves, what happens is there's going to be low spots and high spots. So we're going to pick up some of this water and stick it on the high spot, except we are going to assume, just because it makes our life very simple, that the wave is square. I know, a square wave. That's ridiculous, but whatever. This is apparently what their equation they give you is dependent on. This is why it took me so long to figure it out, because it didn't occur to me that they would use a square wave. Okay, so we are going to take some water. We're going to take it from the low spot, lift it up. So here's equilibrium, right? Here's the crest, here's the trough. Here's the crest, trough, right? And that's what we're going to use in order to calculate the energy. And the energy starts off as gravitational energy, or the energy to lift this chunk of water up to the top so we can have our nice wave, okay? So we say, all right, so this is just mgh, where the mass is the mass of this chunk of water that we lifted up. Okay, so the h will be the distance that we lifted up, so we'll take it from the center of where we lifted it up to the center, or of where it was to the center of where it is now. That will be our height, okay? And we can see that the height is really just the amplitude. So from center to center is the same as from equilibrium to the top. So we're going to replace h with a in our equation, where a, warning is amplitude. I know in a lot of other equations a is area, but in this particular one you need to remember that a is amplitude. Then we got to calculate the mass. Well, the mass of this object is going to be the again, the density, or rho, times the volume. So we're going to make some substitutions. So we take our mass and we plug in write the stuff in, and we get this equation over here. And then we're going to say, all right, so how do we calculate the volume of this thing? And we say, okay, this is just a giant rectangle. So the height of the rectangle is the amplitude, right, from equilibrium to the top. We say the length of the wave is L. Okay, this is the length like along the beach, right? If here's a beach and here's some Billy guys sunbathing, and here's the beach and the length of the wave, right, as it comes in. So the length is L, and the width of the wave will be half a wavelength, right? So a wavelength goes from crest to the second crest. So that's this is only going to be half of that distance. Okay, so we have here the volume, and we're going to plug all this crap in, and then our equation just starts to look horribly ugly. Oh, you know, one thing I forgot to, oh yeah, no, that's all good. Okay, so then we're going to do our last couple of steps where we say, okay, period, so the time, right, we plug in as the period, because that is the time to do one cycle. And we're going to say, okay, the period we know to be wavelength over the speed of the wave. So we'll make another horrible substitution, and we get wavelength on the bottom. Velocity will move up to the top, and since the wavelength is on the bottom, and there's already a wavelength up here, the two wavelengths will cancel out, and I'm left with all this stuff right here. Now this is the power that is generated by this wave then, if all that gravitational energy turned into whatever you need. However, we don't usually write it in terms of power, because oftentimes it depends on how wide our oscillating water column is, right? If we have a very narrow station, it's not going to harness much of the length of this wave. So if here's the beach, right, and we have a building right here that is our oscillating water column, if it's a very narrow building, we're not going to get much energy out of it. If it's a very long, wide building that takes up much of the beachfront, then we'll get a lot more energy. So what we're doing is we usually, when we do wave energy, we calculate the amount of what we call the power per unit length, or power divided by length. So the length that was over here, we just divide it by both sides, and this quantity right here, this whole quantity, is called the power per unit length, or that's the energy per length of the wave. And depending on how wide or long how much beachfront your oscillating water column takes up will depend on how much energy you can actually get out of this. Okay, so here's your equation, right, where again A, warning, A is amplitude, not area in this equation. It's the amplitude of the wave, rho is the density of the water, g is your gravitational constant, and v is the speed of the wave. And this is your calculation. And again, don't forget, this is a stupid calculation because it assumes it's a square or rectangular profile of a wave. Dumb, but what can you do? All right, so is this equation in your packet? The answer is Yes, it is. So it is the second one. And notice they just write out power per unit length. That's just power divided by length, okay? So this is power per unit length. You've got to remember the first one's just for windmills. The second one's just for wave energy. And then you have to remember how to do the hydroelectric, that you're just turning gravitational MGH into power. So MGH divided by time. So there it is. Yes. Whatever. All right, here is a sample problem with waves. So let's say we want to calculate the power per unit length, and we have the amplitude to be 5 meters, and the speed is 4.8 meters per second. And let's say it's in the ocean, so the salt water, and the depth of, or sorry, the density of salt water is this amount right here, 1,140 kilograms per cubic meter. Okay, and so we want to calculate the power per unit length of this wave. Okay, so we're going to use our equation. We just plug in our numbers. So A, remember, is amplitude. V is the speed of the wave. When we plug in the density, we just plug and chug, right? So all the numbers go in, and we get an answer of this amount. So 671,004 joules is our power per